welcome to the CERIAS seminar for November 18th, 2009. It's my pleasure to introduce Professor Gerome Miklau, who joins us from the University of Massachusetts. Dr. Miklau, 4 years back, obtained his PhD from the University of Washington, working with Dan Sushiu, and actually at one point was working on a joint project with some of us here at Purdue. Among other things, Professor Miklau has the distinction of being the first winner of the ACM Sigma Dissertation Award. So we're very honored to have him here with us, and we'll hear about his new work going on in analyzing private network data.
Thanks, Chris. Hi, it's good to be here. My name is Gerome Miklau. As Chris mentioned, I'm presenting joint work with our graduate students Michael Hay and Chao Li, and some faculty collaborators at UMass Amherst, David Jensen and Don Towsley. We also collaborated with the University of Washington on parts of this work. Vibha Rastogi and Dan Sushiu are our collaborators there. Please stop me at any time to ask questions. Don't be shy about that. So this talk is about social networks, technological networks, any data that looks like a graph. So I like to start out with some concrete examples of social network data. The graph that you see here is a very famous social network. It's commonly called Zachary's Karate Club. If you've read the social network literature at all, you may have encountered this graph. It was data collected by a sociologist named Zachary, who went around to every member of the karate club and asked each member who they were friends with and drew this graph to study the formation of communities and how community formation evolved over time. So it's a rather small social network, but an important one that people are still using as a kind of base case for algorithms that they study. This is another social network, one that's a little more sensitive since privacy is the focus of this talk. This is a social graph based on romantic connections amongst high school students. This is part of another sociological study where I believe they were studying the structural patterns that evolved in such a social network. They were observing things like there's one big central ring that you see here, but other than that, there's a lot of tree structures in the graph. Here's another example of a highly sensitive network data set. It's a community of drug users and sexual partners in Colorado Springs. This graph was used to study disease transmission, the transmission of HIV in a community, which is highly determined by the topology of the graph. Okay? This is a recent data set that, very recent data set that was collected by monitoring mobile phone users and inferring links based on the location of users and their communication over mobile phones, and they were comparing that with self-reported friendship links to understand whether people accurately report friendship and how it corresponds to who they actually come into contact with. So those are all examples of social network data. Some of aspects of the data is more sensitive than others. Those are all relatively small graphs that I can make pictures of for a talk like this. But these days people are also collecting truly massive graphs. So this was a World Wide Web conference paper from 2008 which studied instant messaging traffic through Microsoft Messenger, I believe, was the platform. And this network consisted of 180 million nodes over 1 billion edges. Okay, so we can't even visualize this network. It's too large, but we can study its properties, and this paper looked at a number of properties there. So we'd like our privacy mechanisms to be able to scale to the massive graphs that are collected these days. So coming back to the issues of privacy, each of the graphs I showed you may be more or less sensitive, and I'll talk in a moment about what is sensitive in a social network. But let me just point out here that privacy is a major obstacle to the dissemination of this data. Getting this data to the people who need to analyze it is a hard problem, and it's often an obstacle. So one of the things that may happen is that analysts just can't get the data that they want. The data is collected and it's stored somewhere, but the analysts aren't able to study it. If that doesn't happen, we may be able to work out limited availability. So within the institutions that own the data, some people analyze it, but or they may make some limited agreements with certain people who get to study it. Or we may have availability, so data is available, but at some cost. So the cost might be a privacy cost to the participants in the data set. An example is a very common data set is the Enron email corpus. So email data sets are hard to come by because people care a lot about the privacy of their email transmissions to other people, but analysts would like to study real email data sets. So one of the few data sets that is publicly available is only available because Enron got sued and the lawyers posted on their website transcripts of subpoenaed email. So the cost to privacy of the managers at Enron was severe. There were a lot of sensitive information in that data set. Maybe you don't care because they were managers of Enron and they violated the law, but still, sometimes we get important data sets only as a result of violating people's privacy. In other cases, we have data sets, for example, crawls of online social networks, but they are biased because operators of online social networks don't really want us to crawl their data sets, and so there are some mechanisms that prevent us from crawling them accurately, and that introduces bias. So getting data to analysts is hard. And the overarching goal of our work in this area has been to understand the extent to which we can permit accurate analysis of graph-structured data without violating sensitive information about participants. So to date, we have focused on topological properties, means the structure of the graph, and not so much on attributes that may appear on nodes or on edges in the graph. So I'm going to talk today about two specific tasks that we've studied. The first is the degree distribution of a graph. I'll describe these later. And the other is motif analysis. But other things that we would want to study on a network topology would be the community structure, how communities form in the graph, where the communities are, simulate processes on networks like routing, search, the spread of rumors or infection, and the resiliency of networks. And we're moving towards those analyses now. So in the remainder of the talk, what I want to do is paint a little bit of a high-level picture of what people are doing, because this problem is getting attention in the literature over the past 3 or 4 years. What people are doing in terms of protecting network data. Then I'm going to present our work on specific tasks, and it's going to use a notion of privacy called differential privacy. Some of you have probably heard of it, but many of you may not have, and so I'm going to review that in some detail. And then I'll present the main technical chunk of the talk is on the estimation of degree distribution. Then I'll quickly go through some details about motif analysis and wrap up. Again, please stop me at any time if you have questions. So here's a toy example of a graph, and we see that there's a node table. The node table is kind of the classical form of data that we've thought about protecting before. So each entity is a row in that table, and maybe some of the properties of those entities are sensitive, and we would want to safely publish aggregate properties of that population without revealing one particular row. Now, when we have a graph, we also have an edge table, and the edges are also sensitive information. So an identified edge in a social network may be a sensitive fact that we need to protect. The fact that Alice talked to Bob can be sensitive in some of the networks I showed you earlier in the talk. There are also implied properties of the graph. For example, the degree of an individual could be sensitive. In a collaboration network, you might want to advertise your high degree. In a romantic network, you may want to advertise your low degree or hide your high degree. In addition, implied properties that are implied by the connections in the graph can be sensitive. For example, you may want to hide the fact that most of your friends are Democrats. Okay, or that most of your friends are over age 50. Okay, properties like that can also be sensitive. So what is sensitive in the data set that represents a graph is more complicated than tabular data that is common to the census or some classical settings. It's part of the challenge that we face in protecting this data. So one of the first things that we try is when we try to protect, and people often think of this, when you try to protect a network, is what we call naive anonymization. So